That's to my person. And now I'm going to start with my presentation. So the agenda for my part today is that we start with a short motivation. Then I give you a short introduction into SOTIF and functional safety. Then I want to provide an overview of the organization of SOTIF activities. Then AI-specific content of ISO 21448 and a short summary. Everything I show today is based on the latest version of the ISO, so the ISO DIS version. The final draft is still in the balloting phase, and hopefully the release of the ISO 21448 will come this year in summer. So what are the intentions of SOTIF? First, automated driving, of course. SOTIF is doing something for automated driving, and automated driving is not a matter of if, furthermore, it's a matter of when. And with automated driving, there will be an impact on nowadays vehicle architectures. And this results in new technologies with new or changing risks, which are currently not known completely, e.g., artificial intelligence and machine learning. And we have also an increase of complexity. So we have a higher degree of networks and therefore more interfaces. So the good thing is that functional safety and safety of the intended functionality based on ISO 26262 and ISO 21448 provides methods and tools to cope with the coming requirements. So as I said, when we talk about SOTIF, we have also to talk about automated driving, and this table is taken directly out of the standard with some additions from us. And here you can see the levels of driving automation and some more information for that. So we have the SAE level 0, which means that we have no driving automation. So the lateral and longitudinal vehicle motion control is performed by the driver, and the object and event detection response, so the sensing of the environment and the situations and scenes, is also done by the driver, and of course fallback is also the driver. So operational design domain here is not available, or let me say not applicable. Then we have level 1, driver assistance. So the lateral and longitudinal vehicle motion control performed by driver and the vehicle or the system. The sensing and detection is done by the driver, and fallback is also driver. And here we have a limited available operational design domain. Then we have level 2, partial driving automation. So here the control of the vehicle is completely done by the vehicle and the systems of the vehicle. The detection is done by the driver, and the fallback is also the driver. And now we start with levels of automation where it's getting interesting, concerning also for AI ML specific topics. So for level 3, we have conditional driving automation, and there the vehicle is responsible for the movement and also for the prediction of the environment. But good thing is that we have here as a fallback, when something is wrong, we can hand over, but here it is very important to know we have to hand over to a prepared driver. So the driver is allowed to do some other things like reading a book. So we need to give the driver time to get prepared to take over the control. ODD also is limited available. Then level 4, high driving automation. So here we don't have the fallback of driver. So here the vehicle needs to provide all functionalities also when the situations are critical. The only way of restriction you have here is by limiting the ODD or the area of application. And at least level 5, full driving automation. Here, the ODD is unlimited, so the vehicle needs to do everything in nearly every environment. So what is the operational design domain? And here I take the definition of SIE J3016 because the definition in the SOTIF standard is not so precisely. I think this definition is a bit more elegant, let me say it like that. And the ODD is the operating conditions under which a given driving automation system or feature thereof is specifically designed to function, including but not limited to environmental, geographical, and time of day restrictions, and or the requisite presence or absence of certain traffic or roadway characteristics. So what does it mean? When the ODD is unlimited, we have a limit, of course. The limit is the world. So cars are not going to space. So we have a kind of limitation, which is our world. And the operational design domain is, let me say, a restricted set or outcome of the world. So what we can do is we can do restrictions concerning the roads where the function is allowed to work. So for example, only on highway and not on country roads, not on city roads, not off-road. We can also put in restrictions concerning the vehicle speeds which are allowed, or environmental conditions like no snow and ice, no high temperatures, or no wet roads or something like that. So there is no, there will be no one ODD that fits all instead of level 5, which with the unlimited ODD. Till level 4, we will have a limitation of the area of application by restrictions. We can specify where the function shall work. So the conditions which are used for an ODD are not fixed, and they shall be specified with respect to the vehicle or the function which shall be realized. The ODD can be limited for SAE levels 1 to 4 and is unlimited for level 5. So let's start with an introduction into SOTIF and functional safety. So question is there a versus? So do we have the situation that we have SOTIF versus functional safety? When we have a look on the definitions for SOTIF is absence of unreasonable risk due to hazards resulting from functional insufficiencies of the intended functionality or its implementation. We have a definition for hazard, which is a potential source of harm caused by the hazardous behavior of the system. And we have a definition for functional insufficiencies. And these are insufficiencies of specification, for example, incompleteness, or performance limitations, for example, of technical capabilities of the intended functionality. And the intended functionality is a specified function on vehicle level. When we have a look on ISO 26262, it is absence of unreasonable risk due to hazards caused by malfunctioning behavior of EE systems. Unreasonable risk is risk judged to be unacceptable in a certain context according to valid societal moral concepts. The term hazard is equal in both standards, and the malfunctioning behavior is a failure or unintended behavior of an item with respect to its design intent. And of course, EE system is a system that consists of electrical or electronic elements, including programmable electronic elements. At least it is a set of sensors, controllers, and actuators. So what you see here, that SOTIF is inherently a part of functional safety, and therefore SOTIF and based on ISO 21448 is a logical complement to functional safety as specified in ISO 26262. So what are causes for unreasonable risk? So when we have a look on ISO 26262, we have to observe the malfunctioning behavior of ES systems at vehicle level. So it could be unintended acceleration, deceleration, loss of acceleration, loss of deceleration, or in general, unintended vehicle motion. When we have a look on the functional insufficiencies at the vehicle level based on ISO 21448, there we have incompleteness of environmental specification, for example, temperature areas, and incorrect specification of maximum vehicle speed or vehicle weight, for example. And we have the performance limitations, which can be limited and not considered perception range of sensor, or overestimated and therefore limited braking assistance, for example. So dangerous situations due to functional insufficiencies in accordance to SOTIF standard can lead to the same or more severe hazards as from malfunctioning behavior in accordance with ISO 26262, or they can cause new, previously unknown hazards. So let's talk about the safety issues causality classification scheme, which shows directly which is part of ISO 26262 and what is part of the SOTIF standard. So in general, we have functional safety issues. These are subdivided into causality class 2, which is related to random hardware issues, so random hardware faults. And we have causality class 1, which means systematic related issues. And this class 1 can also be subdivided into class 1.1, where we have issues with the specified nominal behavior on vehicle level, and class 1.2, issues with the implementation of the specified behavior. So these aspects, what you see here, these are in focus or in scope of ISO 26262, and these are in focus of These are in focus of ISO 21448. So if a certain safety issue cannot clearly be classified as an issue for SOTIF or for functional safety, then both standards. Can you please mute the microphone? I can hear voices.
Which is the root cause of maybe some issues not noticed performing this.
Can I hear voices? Okay, now muted. Now I hope you can hear me again. So if a certain safety issue cannot clearly be classified as an issue for SOTIF or for functional safety, then both standards can be applied in combination to address it. So how are the SOTIF activities linked to ISO 26262? And what you can see here is that here we have the activities of the V model of ISO 26262. And here we have the SOTIF related activities. So the first thing we have to do is specification and design based on clause 5 of ISO 21448. And this is linked to the complete left side of the V model. So item definition, HARA, FSC, TSC. Then we have the SOTIF related hazard identification and risk evaluation, clause 6. This is linked to HARA, FSC, and TSC. Then we have the identification and evaluation of functional insufficiencies and triggering conditions. This is linked to FSC, TSC. Then we have functional modifications to reduce SOTIF-related risks. This is again linked to the whole side of the V model. Then we have evaluation of known potential hazardous scenarios, which is linked to the right side of the V model of ISO 26262 to integration and testing and safety validation. And then we have the acceptance criteria for SOTIF release, which is linked also to integration and testing and validation. And then we have the exploration and evaluation of unknown scenarios, which is linked for the assessment and after SOP, of course. And linked through the whole V-cycle, we have the definition of the verification and validation strategy. And what you can see here is that we have addressed almost documents on the system level, not the hardware software level. So the SOTIF standard, the most impact of the SOTIF standard we have on the vehicle and system level. And the requirements which are derived downwards to or refined downwards to the hardware and software level will not be different to the requirements we know from ISO 26262, for example. So let's talk about the standard itself. Title, Road Vehicles, Safety of the Intended Functionality. The actual version which is available is the draft international standard. Still valid version is the ISO PAS 21448 from 2019. And this presentation is based on the DIS version from 2020. Just a hint for you, the PAS version has 68 pages and the DIS version has nearly 180 pages. Normative content are the clauses 5.1, 6.1, 7, 8, 9, 10, 11, 12, and 13 with their work products. All other clauses are only informative. And which is also new in the DIS version, we have tables there. And the intention of the tables is to support the development activities by providing measures and methods which can be used for specific activities. But the methods and measures listed in the tables are not weighted regarding their priority of application. So the tables you know from ISO 26262, where we have recommendations of use, this you will not find in the SOTIF standard. What is the scope? Standard provides guidance on measures and activities for the following development phases. First is specification and design. So for example, when you specify a brake function, which shall provide the correct braking force with respect to different road friction types like wet or icy roads. Additionally, reasonable foreseeable misuse, which could lead directly to hazardous behavior, shall be considered here as a triggering condition. Then we have the phase verification. So reviews, test cases, which cover all relevant scenarios or injection of potentially dangerous triggering conditions. Validation, for example, long time tests, and operation field monitoring of SOTIF incidents. And this is for functionalities where proper situational awareness is derived from complex sensors and decision or processing algorithms, for example, for automated emergency intervention. The standard is applicable to an intended functionality where proper situational awareness is essential. And the standard says that it can be used for automation levels 1 to 5. I personally disagree with that. The standard fits very perfect for level 3, not so perfect for level 4. And from my personal perspective, not for level 5, but it's my opinion. So compliance with local driving laws, policies, or other road norms is excluded, but cases where not following laws and rules of the road could lead to safety hazards are in scope. Sorry. Other safety domains, for example, hazards caused by other technologies like mechanical systems are excluded. For these, you shall use other standards, like, for example, coming from Machinery Directive, EN ISO 12100, and so on. And hazards caused by attacks, so security hazards, are also excluded. Therefore, you have to take a look into ISO SAE 21434. So ISO 26262 assumes that the intended functionality is safe and addresses EE system faults. that can cause hazardous behavior due to a deviation from the intended functionality. And ISO 21448 provides measures which confirm, hopefully, this assumption. Let's have a look for the relevant topics addressed by different safety standards. So we have the system level, and EE system failures caused by random hardware faults and systematic hardware and software faults are in the scope of ISO 26262. Insufficiencies of specifications, performance limitations, insufficient situational awareness with or without misuse are scope of SOTIF standard. Incorrect and inadequate design of human-machine interfaces is part of the SOTIF standard and the European Statement of Principles on HMI. And system technologies, so other technologies are linked to specific standards like the standards from Machinery Directive, or here for battery management systems, the ISO 6469, for example. Then we have external factors. The misuse, direct, indirect, is part of SOTIF. Security is part of ISO SAE 21434. Impact from active infrastructure and vehicle-to-vehicle communication is part of SOTIF and ISO 20077 and ISO 26262. And impact from vehicle surroundings, so other users, passive infrastructures, and so on, is part of both ISO 21448 and 26262. So let's talk about organization of SOTIF activities. SOTIF follows three principles. First one is the SOTIF related hazardous event model. Then we have the 4 area scenario categories and the sense plan act model. The hazardous event model, we have the triggering conditions in known scenarios or in unknown scenarios. Triggering conditions also include the misuse. And this will lead to hazardous behavior of the system resulting from insufficiencies of specification of the intended functionality on vehicle level or performance limitations on EE element level or system level. This will lead to hazards, and in combination with a scenario containing operational situation in which the hazard can lead to harm, we will have the hazardous event, and combined with involved persons or their reaction, we will lead to harm. So this model is similar to the model of ISO 26262, but here on input side, the difference is that we have here the malfunctioning behavior of EE systems, which is caused by random hardware faults and systematic hardware and software faults. So example, how to identify hazards. So we have a scenario and a triggering condition. For example, we drive in a city with high speed, radar reflection and shadow of a bridge detected and classified as a static obstacle on the street. Here we have to take care about the occurrence over the operating lifetime. And to the system automated emergency brake, we have the hazardous behavior that the AEB requests braking resulting from functional insufficiency. Bridge is classified as an obstacle. Then we have a hazard 1, collision from behind is possible in a scenario that we have presence of rear traffic, for example, a vehicle following the ego vehicle very closely. And we put here the exposure known from ISO 26262. This will lead to a hazardous event. So presence of a vehicle closely to ego vehicle during unintended braking. We add here the reactions of involved persons, like driver of following vehicle cannot react in time because distance is too close. We add here the controllability from ISO 26262. This will lead to a harm. Driver of ego vehicle and following vehicle gets injured due to a crash. Here we add the severity known from ISO 26262, and this is one risk. And the second one is that people falling from their seats down on the floor. Scenario is that people are sitting with unfastened seatbelt or standing in a shuttle bus. Then when we have this hazard, persons cannot prevent fall by holding on to a handle or other fixed objects. And this will lead to a harm that people get injured due to falling down on the floor. And all things together will lead to an overall risk of the functionality. Then we have the 4 area scenario categories. Scenarios which are part of relevant use cases are subdivided into 4 areas. Area 1 are known and not hazardous scenarios, which are green. Area 2, known and hazardous scenarios, orange. Area 3, unknown and hazardous scenarios, red. And area 4, unknown, not hazardous, is yellow. So this model is a conceptual abstraction representing the goal of the SOTIF process, which is to perform a risk acceptance evaluation of area 2 based on the analysis on the intended functionality and reduce the probability of known scenarios causing hazardous behavior in area 2 to an acceptable level of risk. And this leads me to the question from the beginning. This is exactly the type of how to say how good I have to be. We have no KPIs, no quantitative targets here. And we have to reduce the probability of the unknown scenarios causing potentially hazardous behavior in area 3 to an acceptable level of risk. So ultimate goal of SOTIF activities is to evaluate the potentially hazardous behavior present in area 2 and 3, and to provide an argument that these areas are minimal, respectively below the specified acceptance criteria. So we want to change this to this. And it is expected that the residual risk will be reduced in the areas 2 and 3, and the confidence of safety will be increased by the growing scenario set in area 1. So summary of the activities, area 1, here we want to maximize or maintain the set of known scenarios while minimizing areas 2 and 3, retaining or improving the safe functionality. Area 2, we want to minimize this area with technical safety measures to an acceptably low level with statistical significance. And we evaluate the potential risk and move the hazardous scenarios to area 1 by improving the function or restricting its use. It's also an option, but we can do. Area 3, we want to minimize this area as much as possible with an acceptable level of effort with statistical significance. The problem is that we don't know how many unknowns we have. So the question, what is acceptable level here when I don't know what is the whole amount of these areas or hazards, makes it very difficult. And area 4, if unknown, not hazardous scenarios are discovered, they can be documented and reported, and this helps to minimize area 1. The last principle, sense, plan, act model. The hazards behavior is closely related to the performance of sensing the environment, planning of actions by using decision algorithms, and providing an action where the HMI is included. And to provide the intended functionality correct and safe, we always have to talk about sense and plan and act. So the appropriate selection of capable system architecture is very important consideration to ensure SOTIF and overall capability and corresponding activities take place both at early stages and throughout the whole development lifecycle. So what you can see here is the flow of SOTIF activities. So we start with the specification and design, then analyze the hazards and risks. And if the harm is reasonable, we go to a review and when the risk is reasonable, we can directly go to operation phase. If not, If not, we have to identify and evaluate the insufficiencies and triggering conditions. And when the expected system response to triggering conditions is accepted, I can go to the acceptance criteria, and when everything is okay, I can go to the operation phase. If not, I have to go back and have to perform functional modifications to reduce SOTIF-related risks. Then I have to evaluate of known potential hazardous scenarios, which was area 2. And if the resulting risk is sufficiently low, I can go to the acceptance criteria and operating phase. If not, I have to do modifications and make this loop again. Same for the unknown scenarios. When the likelihood of encountering an unknown scenario leading to hazardous behavior is sufficiently low, I can go directly to the operating phase. If not, I have to do some modifications. So when we talk about safety of functions, now we have to do some activities, supporting processes, and of course, a management. And when you want to be complete, you always start with quality management, for example, based on ISO 9001, IATF 16949, or ASPICE, for example. So developing a safe product is not possible without strong basement. So a quality management system or process is absolutely required. Then we have, let me say, general safety management based on standards from, for example, machinery directive to cope with a mechanical safety, chemical safety, electrical safety, and so on. Then we have now the safety of functions, which is now always in combination functional safety based on ISO 26262, SOTIF 21448, and security ISO 21434. So functional safety of ISO 26262 is now only a part of the safety of functions. When you want to make functions completely safe, you have to talk about these 3 standards and this type of management. And on top, for automated driving, we have now a lot of standards which are still in work. For example, ISO TS 5083, I'm part of this group. This is safety and security for automated driving. Then we have ISO PAS 8800, which is AI specific standard for automotive and other standards. So let's talk at the end about AI specific content of SOTIF standard. So safety for machine learning hardware, and following the SOTIF standard for hardware safety of machine learning applications, they say ISO 26262 and SOTIF shall be considered. So to cope with random hardware faults and systematic hardware faults following ISO 26262 part 5. And performance limitations following ISO 21448. Then for software, when I use tools as a part of the offline training process, for example, are handled by part 8 of ISO 26262 clause 11, confidence in the use of software tools. Machine learning is, they say, machine learning is some form of software which generates an output from the input using specified computing operations, like matrix multiplications or discrete convolution or nonlinear functions. And based on this, to this effect, it's by itself not different from other non-learning algorithms and can be verified by conventional means. This means implementation of computing operations can be verified according to ISO 26262 part 6. And functionality of ML software, like performance in object detection, for example, is another aspect. The model and the weights for the model or labels derived from training, which is a data-driven process, can induce uncertainties in model prediction that might constitute functional insufficiencies that are addressed by the SOTIF standard. The identification and mitigation of ML limitations due to built-in biases or incomplete training sets can be part of SOTIF processes. And you can use part 6 Annex C for ML trained weights. Calibration data in the context of ISO 26262 is used to adjust the behavior of known model, where the weights of the ML model are used to define the model itself. So summary, a new version of the SOTIF standard, which is substituting the past version, is expected to be released hopefully in summer this year. SOTIF is a logical complement to functional safety by adding the aspects of functional insufficiencies and performance limitations. By covering the levels of automation 1 to 5, SOTIF is the link between classical safety topics and safety for automated driving. And the usage of AI ML-based functionalities will introduce new challenges also for the techniques and measures for safety. The classical approaches of functional safety and SOTIF can partly be used as seen before, but especially for deep neural networks, which are often not traceable and or non-deterministic, we need to start to discuss how these architectures can be safeguarded. If you want to learn more, have a look on our training options. I want to say thank you for your attention, and now I'm open for questions.
Hi, thank you very much, Martin. I think we're going to save the questions right till the end so that the three of you can all get together and answer the questions from our audience. At the moment, there are very few questions coming in. I think we've got 2 questions now.
I hope because it was not so bad.
No, maybe you answered all their questions, right? Maybe all of their questions are answered. I doubt it. I think people are being shy. Come on, ask the questions. We'll try and answer them at the end. I think we should move on, though. We should move on to the next presentation from Kemal. Is he available? Thank you, Kemal. I'll let you introduce yourself.
Of course, no problem. I have an introduction slide, so when I come to that, I will introduce myself. Hello, everyone. My name is Kemal Ure from Eatron Technologies and Istanbul Technical University. First of all, I would like to thank the organizers of the club for inviting me to this event. I'm really happy to be here, and also I would like to thank Martin for the very informative the presentation. So today, what I'm going to talk about is actually a little bit different, maybe a little bit orthogonal to what Martin has been speaking about. I'm going to talk about algorithmic approaches to how to perform safety and performance verification, especially for machine learning-based automotive applications. So most of what I'm going to talk about today is definitely not industry practice right now, but it is more about preliminary work in how to address the challenges in verifying the performance of these very advanced algorithms, because it is clear that the conventional approaches to verification is definitely going to have a hard time verifying these algorithms, especially advanced decision-making and perception algorithms. So I'm going to talk a little bit about, for example, what kind of research we are doing in this topic. And you will see that most of the stuff we do is actually coming up with algorithms to address this problem. So that is what I'm going to talk about today. So about myself, my name is Kemal Ure, and I'm the Director of Artificial Intelligence at Eatron Technologies, and I've been very fortunate to be involved in the company since its inception at 2018. And I will talk about Eatron a little bit in the next slides, but we are basically an automotive startup. We are a software startup focusing on electric and autonomous vehicles. So besides my duties at Eatron, I am also a professor at Istanbul Technical University. Before that, I got my PhD from MIT, and I've been working on autonomous systems for a while now. I would say I've been working on autonomous systems for maybe close to 15 years now. And I'm a professor of artificial intelligence and data engineering department. And the main research I do is basically on deep reinforcement learning, and especially applications of that to autonomous systems such as self-driving cars and unmanned aerial vehicles. And me and my group, we also do a lot of research on large-scale optimization as well. So that's my bio. So a very short introduction to Eatron. So we are a startup and where our offices are mainly based on Warwick, UK and Istanbul, Turkey. But recently we have also opened offices in China and India. And we are a software startup focusing on electric and autonomous driving technologies. Right now we are close to 100 people, and our two main products are called BMStar and IMStar. So one of them is a BMS software, which has a lot of AI functionalities. Then the other one is a motion control system, IMStar, which also has a lot of AI functionalities. So just briefly to talk about this, in the battery management systems, what our AI systems are doing are basically doing smart battery cell diagnosis and remaining useful life prediction. And we are basically developing a lot of machine learning software to perform these tasks very accurately. So, and by using data from lots of different resources. And basically we can highly accurate what is the remaining useful life on your current battery, or if something goes wrong with your battery, how you can diagnose that, etc. And the other product, IMStar, is basically, it is like an ADAS system. So we have got a perception system installed on the vehicle, and it can actually detect road conditions, whether the road is bumpy or whether, there's some kind of, there's a hole on the road, or there are, dangerous driving conditions, and it can automatically adjust the motion control software, the suspension control system, to accommodate for that. So it is a combination of perception and decision-making, AI. So these are the two products we have, and we have been applying AI to them a lot. And obviously, addressing the performance verification and safety is a big challenge for us, and we have been actively working on that too. So first of all, I'm going to take a look at a little bit of the general scene regarding the autonomous vehicles technology. So why it is so hot right now. So what are some of the recent advances? Since I know this audience is actually very well versed in that topic, I'm going to keep this stuff short. And then I'm going to move into more the technical part, like what are the challenges we have in verification of safety and performance of these autonomous vehicles? What are some of the algorithms that are out there? What are some of the approaches for verifying the performance? And then finally, I will talk a little bit about the research we do at Eatron Technologies in order to address these problems. Okay, maybe this doesn't need the introduction, but of course, we all know that autonomous driving technology, there were tremendous improvements in the last 20 years, maybe more so in the last 10 years. So now we've got perception systems that can simply look at, the road, and they can infer the state of the traffic. They can even predict how the traffic is going to flow, whether, there are pedestrians on the scene. Are they going to, make some hazardous moves? We also have amazing perception, decision-making and control systems that can very accurately control the car up to some specifications. So these were kind of like dreams, 20, maybe 30 years ago, but now it's a very strong reality. And this is mostly due to advances in sensors and algorithms, especially advanced sensors and hardware. They came a long way. So now we can collect much more reliable data. We can process data much more reliably. But on top of that, we also had amazing algorithmic improvements in the last 10 years, mostly thanks to machine learning and especially deep learning. So advances in deep neural networks, the algorithms and the way we trained them enabled us to solve perception and decision-making problems to unprecedented levels that we haven't seen before. And if you look about the promise of machine learning, like why machine learning is so useful for a problem like this, I mean, this is actually my personal opinion. Different people might find different uses of machine learning, but to me, the biggest advantage of using a machine learning system, it actually kind of frees you from writing these, conditional statements in your software. So whenever you engineer a system, using a classical way, that system is only good up to your specification of your parameters. So the system is not going to work right all the time. So what you need to do is you need to write all of this, conditional if else like statements, right? You are going to say that, well, there is this edge case. if we encounter this edge case, we are going to use these parameters. If we encounter another edge case, we are going to use that set of parameters. So whenever you are dealing with a classical engineering system that is going to operate in a very uncontrolled, complex environment, like driving an autonomous car, then we need all of these conditions. But the main premise of machine learning is, let go of your heuristics, let go of your manual detection, just parameterize your software and let that parameters be inferred by using machine learning. So instead of relying on hand-coded statements, we let the data speak and tell us how should this software actually behave. So, and of course, that is great, that is amazing, and it seems to work well up to some point. So we will discuss that. Of course, it doesn't always work as intended. But mainly, this actually allowed us to, build amazing perception and decision-making systems. And not only in autonomous driving, but also in other automotive technologies as well. For example, in better management systems, the kind of predictive systems we are using right now, we weren't able to, we wouldn't be able to build them like 10, 15 years ago. But because of the availability of data and algorithms, now we can do it. So basically, yes, artificial intelligence is transforming the automotive industry. And of course, again, everybody knows about this. This has a lot of benefits, especially in the environmental and social impact. Usually autonomy and electric vehicles, they go hand in hand together. So there's also a lot of environmental benefits, but of course, the improved safety is, again, one of the main advantages, right? Because in theory, automated car should be more safe than, human driver if we did everything right. Because computers can process information much reliably, much more quickly, and they can also execute decisions much quicker than us. So in theory, if we do everything right, an autonomous vehicle should be more safe. And similarly, because autonomous vehicle is not making suboptimal tactical decisions, this should also, lead to, improvements in congestion. So again, these are all, potential benefits of autonomous vehicles. And if you look at some statistics, we can see that, the market in autonomous vehicles is also increasing, and also the people's perception regarding autonomous cars, that is also improving. Autonomous vehicles is a scary technology, right? I mean, whenever you say, you are going to get on a car and, that is not going to be controlled by a human driver, that is kind of like a scary thought. The same with aircraft. So, but we can see that if you look at, people's perception throughout the years, percentage of consumers who think self-driving vehicles will not be safe is actually decreasing throughout the years. So people are gaining more trust. And of course, the number of automated vehicles with some level of automation, of course, some of these can be low, such as level 1 or level 2. But again, the number of cars which has these functionalities, they have been, increasing. So all of these statistics are basically telling you that we are going to see more and more self-driving vehicles with some level of automation on the roads. Each year, this number is definitely going to increase. And that actually leads to a very natural question, like how safe is this technology actually? Because when it is only small numbers, then you run into the risk of, small samples. So you cannot really measure the safety by looking at the current numbers because, of course, there are extensive road tests, there are, other kinds of statistics, but the real safety issues are only going to become more and more apparent as the number of, consumers who are using this technology increases. If you look at the current statistics, they are actually going to tell you, great things, especially if you look at the statistics, for example, provided by Waymo. They will tell that, we have driven these cars for hundreds of miles, and compared to people, statistics of cars who are driven manually by human users, the number of crashes or number of fatalities is way, way less. That is what the statistics will tell you. I didn't put actually a lot of statistics here, but if you actually go and look for that, you will see that most of the time, people who are working on this technology, maybe including me, will tell you that this technology is safe. But at the same time, you also keep hearing about, crashes of these vehicles. There have been numerous crashes from Tesla and other, companies. So again, you start to think, how safe is this technology? And this is actually a very difficult question to answer. As again, Martin laid out in his presentation, these are not simple systems. They are actually very complex decision-making systems. And not only that, they are operating in a very uncontrolled and complex environment. For instance, if you are trying to validate a very simple system, such as, I don't know, maybe you are trying to validate the safety of a tire or something, you just have maybe 2 or 3 parameters that you need to check, like how much force I am exerting on this tire, how much torque I am exerting on this tire. So the input space is actually not that big. So when the input space to a system is not that big, it is actually not difficult to come up with a systematic approach to test the safety of the system and then get some, sort of performance guarantees out of that system. And if you look at the classical safety and verification approaches, they mostly work very well with low complexity systems. But when you go into an AI-driven system, such as an autonomous driving system, there are all kind of different scenarios that you can run into. You can have, thousands of different traffic scenarios. Especially when you want to validate this in an urban area, there can be pedestrians, there can be different light conditions, there can be different weather conditions, etc. So the input space is just gigantic. It is too huge to apply the classical and conventional methods. So this is why we need to come up with something more creative if you really want to answer the question, is this system really safe under all, typical operating conditions? Okay, so I was actually, when I was preparing the slide, I was looking for a good diagram where I can actually show, there is this scenario space and there are these hazardous parts and there are these non-hazardous parts. And I couldn't find a good picture. Then in the seminar, actually, Martin ran to my help. So when I was watching this presentation, I immediately saw this figure and I say that, that is actually the figure I was looking for. So Martin, sorry, I just immediately stole this from your presentation, but at least I gave a citation to you. So I'm hoping that's okay. So basically, so that is the figure we want to compute, okay? So we have this software, and this can be any type of decision-making or artificial intelligence software. And we really want to compute this figure because it is not available in the beginning. You have some idea what this figure is going to be in the beginning from your simulations, but when you are designing a system, you only end up doing a small set of simulations usually to get some level of performance out of your system. And after you say that, okay, so the initial prototype is finished, you really want to compute this figure, like under what part in the scenario space I am going to run into danger. And that actually turns out to be a very, very difficult question for an autonomous driving system, because, like I mentioned, the input system is very, very large. So this is the key problem number one. How do we find these failure scenarios? Like, how do I know what are these areas in my scenario space where my system is going to fail? So that is question number one. And the question number two is, given that I have found these failure scenarios, and let's say that they are not at an acceptable level. So my autonomous driving system, my perception system, or whatever, is actually not performing at the intended level. Then how do I fix this? And this again turns out to be a very interesting question for machine learning systems, because in a classical system, if something doesn't work, you simply tune the system. But in a machine learning system, other than some hyperparameters, we don't really tune systems. We need to retrain them, because the performance of the machine learning algorithm at the end of the day actually highly dependent on the data it is trained on. So whenever something is wrong with your machine learning system, that actually means that most of the time you cannot simply get away with tuning your hyperparameters or rewriting your software. You need to find more data, and that actually puts us into a very interesting loop where we need to work on adaptive data sets, dynamic data sets. So we need to continuously assess where my system is malfunctioning. Is it due to lack of data? And go and collect more data so that we can improve it. So like I said, this is usually not a standard industrial practice right now. So this is mostly in the research phase. And basically what I'm going to tell you for the rest of the presentation is what people are doing in regards to this, fixing this problem number 1 and 2, and what are we doing at Eatron. So the rest of the presentation is basically going to be about that. And if you want to actually read a perfect survey, on all of these methods, like algorithmic approaches to verification of safety of neural network-based systems, you can go check out this amazing survey, my friends at Stanford University. Okay, so here's a brief survey, and it is really a brief survey because if you, for example, search for, again, algorithmic approaches or verification of autonomy systems by, black box verification, you will only find a few papers in the past, but it has been picking up. People are realizing that this is actually a very hot problem, an important problem, and there have been a couple of important advances in the recent years. But of course, if you just look at black box verification or verification of machine learning systems, if you go back, you will, in the last 10, 15 years, you will find hundreds, thousands of papers. In here, I'm just going to focus on algorithms which are mainly focusing on verification of autonomous systems, especially self-driving cars. Okay, so it is clear that when we have got a huge input space, then it is really not that possible to test every possible scenario in the space. It would be, because of the curse of dimensionality, it would be infeasible to do it. So for instance, you are trying to verify a very simple ADAS system, something such as ACC, adaptive cruise control. And let's say that the only parameters that you care about is what is the speed of my ego vehicle and what is the distance between me and the car that is in front of me. So in this case, your parameter space can be parameterized as follows, and this can be your scenario space. So everything in here will be a different scenario. And one very simple way to test whether your algorithm is safe or not would be the thing we call grid search. We simply discretize this domain. And if our discretization is fine enough, then we can simply test our algorithm at each of these points. And this can be a simulation verification, or this can be actually a real life test. And mostly it is, of course, going to be a simulation because we cannot afford to do this amount of hardware tests in real life. So, but you will see that this grid search approach, it is not really feasible because for only 2 parameters, you will see that maybe you need to run 200 or I don't know, maybe 500 simulations. But of course, these are not only parameters for verifying an ACC system. For example, the speed of the car in front of you is also a parameter. If you add that, you will have a third dimension. And there can be other effects, such as, for example, the weather conditions, the road conditions, etc. And every time you add an axis here, the number of data you need to collect is going to increase exponentially. So because of that, we never, almost always, not use grid search methods when we are trying to verify a system like this. So instead, we need what we call an adaptive sampling strategy, where first we are picking up some random particles inside our search space, and then we look at the safety at those particles, those sample scenarios. And let's say that if some of the scenarios look very, very safe, then we say that, okay, this region is actually safe. I don't need to sample from that anymore. Because for example, if my vehicle is operating, in an acceptable manner in this part of the scenario space, based on the samples, most likely it is going to, operate well in other points as well. What we want to do by sampling, we want to find the failure scenarios. For example, if we find a particular failure scenario in our scenario space, I'm going to keep sampling more from that part of the space because that's an interesting part. That is where the failures happen. So all of these algorithms, what they want to do is they want to find the danger zones and then pick more and more samples out of them so that we can go back and we can say that, okay, now I know this was probably in an unknown hazardous area, and now I can move it into a known hazardous area. So that is what we want to do at the end of the day. In the beginning, this part of the graph is very, very small. And by using these algorithmic approaches, we want to enlarge this part. And if this part is not in an acceptable level, that is where the key problem 2 enters. How can we take weights from this area and put it into the not hazardous area? And that part will come later. Okay, so sampling approaches, so that they are actually the main methods that we use in order to assess system safety for complicated problems like this. And there have been a lot of different sampling strategies. So this is not going to be a too technical presentation. So I'm not going to go into the details of these algorithms. But of course, people have been working on different algorithms, and there's been recent publications on these topics. For example, very recently in 2021, So there was this work on verifying the safety of the OpenPilot. So OpenPilot, as the name implies, is an open source autopilot that you can just download and put it in your car, and it can, handle a lot of nice automated driving, functionalities. It mostly works on an end-to-end manner. So in this work, what they did is they took the OpenPilot, and of course, you cannot always afford to do a real hardware test. So they tested it on the simulation, which is Carla, a very popular open source simulator. I'm sure most of you heard about this. So the question here was, so if I put the OpenPilot hardware on Carla in a simulated system, by using sampling strategies, can I find the conditions where this OpenPilot is going to fail? And in this particular scenario, particular functionality, we are looking at camera and radar as inputs, again, very popular inputs for autonomous cars. And you can see that it kind of works in an end-to-end manner. And after applying neural networks to both of these inputs, we fuse them and we do both longitudinal and latitudinal control. And in this case, what they are going to look at is, for example, what is the maximum velocity, what is the different light and weather conditions, what are the NPC behaviors, for example, the behaviors of pedestrians, etc., and what are the level of sensor noises that we can tolerate in order to make this work. So they are actually trying to search this huge state space, scenario space, and they are trying to find the conditions when it's going to fail. And by using some combination of the Monte Carlo strategies that I've briefly talked about this in here, they were actually able to show that, for example, whenever the sun is striking directly to your camera, so in the dash cam, you can see that the sun is starting to blind you, then most of your perception actually starts to malfunction. And if there's a car ahead of you, but it's a bit far away, then you are fine. So in this case, even though your perception system is not working in optimal performance because the other car is far away, in this type of scenario, you should be fine. But whenever the sun is blinding you, and whenever this car is exactly this amount of away from you, then this is going to lead to unsafe behavior because you are not going to detect the car in front of you, and then you are going to fail. So, so you can try to manually engineer this kind of scenarios, but like I mentioned, there are thousands of different parameters. So it's actually very difficult to engineer a scenario like this manually. But these algorithms, they can search this space very efficiently, and they can tell you, hey, your algorithm is going to fail at this particular scenario. And there are other, approaches and softwares that you can try out as well. There's this trustworthy search engine, which is actually a product of this company, Trustworthy AI. And this is actually an open source tool. You can take your algorithm, take your open source algorithm and send it to them, and their statistical verification engine will run a lot of different scenarios. Then they will change stuff such as road conditions, the different sensor resolutions, looking at different traffic conditions, etc., and they will basically assess whether your algorithm is working intended or not. And if you look at some of the recent conference publications, for example, there's this very nice publication appeared in last year's CVPR. Again, the idea is in simulation, we've got this nice behavior, everything is working as intended. But what if we start to perturb the trajectories of the vehicles or the traffic surrounding us? So by doing smart perturbations, can we actually find scenarios, safety critical scenarios, where your algorithm is going to fail? So they actually show a lot of different scenarios where they can make a lot of algorithms fail. For example, here is an original scenario. Blue is the ego vehicle. And let's say that there's actually a bus in front of us, and we see the bus, and we don't go forward, we actually stop. And there's actually a pedestrian here who is actually crossing in between us. So if this is the original scenario, everything goes as intended, there are no crashes, no failures, but then the optimization algorithm runs maybe millions of simulations and does optimization to find out that if this bus was not here, and instead if you start the bus at this location, and if it goes here, then our car, the ego vehicle, will not see this bus, and they will simply go forward. And it turns out that if they go forward, the perception system actually ignores this pedestrian, and the pedestrian will actually run into this car. So these are all, very interesting scenarios that we need to be aware of whenever we are trying to design an autonomous vehicle system. And like I mentioned, it is very, very difficult to find this kind of scenarios manually, but black box optimization and algorithms can help. So this is one way to do it, and there are also other approaches which are pretty much doing similar things. For example, there's this another work which had been published in Symposium on Software Reliability Engineering. So instead of using classical black box optimization techniques, they are using genetic algorithms in this case. So genetic algorithms are kind of like running millions of simulations in parallel and combining different scenarios to create new interesting ones. So by using different genetic algorithm strategies, again, their algorithm is able to generate interesting crash scenarios based on different safety specifications. So if you're interested to find out more about this type of systems, you can check it out from these references. So instead of just attacking the scenarios, you can also attack your sensors, because again, the sensor noise plays a very, very important part on how much how safe your algorithm really is. And in this particular application, what they are doing is they are fusing camera and radar measurements. And it turns out that if there is some specific amount of noise in your radar, and if there's some specific amount of noise in your camera, when these two meet together, your fusion is going to be worthless. And if your fusion is worthless, even though the surrounding traffic might not be that dangerous, because your sensors are not working as intended, you can again run into collisions. So it is actually very informative to know that given your current sensor limitations, under which specific combinations you are going to fail. Okay, so these are some of the interesting papers from recent years, 2019, 2021. And they are basically showing that using adaptive sampling and optimization approaches, it is useful to find more interesting scenarios. So we have been actively working on this topic too in the last couple of years, and we have been also publishing, but most of the stuff that I'm going to show you today are kind of like preliminary, and we have been also seeing some interesting improvements here in our safety verification systems. And actually, most of the stuff I'm going to talk today is not going to be about only finding these failure scenarios. We are also going to look at how do we fix the scenarios. Because if you look at all of these papers, they find the failures, but they do not tell you anything about how to fix these failures. For example, I know that my sensors are not that good. What should I do? Should I change my fusion algorithm? Should I get better sensors? Or if you look at, for example, in this scenario, let's say that this was an AI agent who made this decision. Okay, now I know that this is a failure scenario, but what do I do? Do I need more data? Do I need to calibrate my algorithm? So we will see that most of the time, the best way to fix a machine learning algorithm is simply train it on more data. And we will see that by closing the loop in here, retraining your algorithms on the data explored by the safety critical part of your scenario space almost always are guaranteed to improve your performance there. So that's actually what we're going to see. Okay, so I'm going to talk about 3 different applications. The first one will be about fixing the simulation gap. I'm sure this is again a term that you already heard before. Most of the AI algorithms are trained in simulations because of the constraints with real life. Constraints on doing real life tests. But then if your simulator performance doesn't match to your real life performance, then what do? I mean, obviously, you need to fix something. So we will be talking about how to fixing simulation gap. And second, we will see that most of the decision-making algorithms, if it is run by an AI, it is usually some sort of reinforcement learning algorithm. So this is not the industry standard, but most of the time, when we are talking about AI making decisions, it means that it is a reinforcement learning agent of some sort. And like supervised learning algorithms, reinforcement learning agents are also prone to making failures if they are not properly trained. So we will be looking at methods where we try to discover when an RL agent is going to make a mistake and how do we fix it adaptively. And finally, we will ask the same questions for end-to-end agents. So again, imitation learning is probably something that you have heard before. If you haven't heard about any of this stuff, no problem. When I start to talk about these areas, I will do a very brief summary of what this stuff are. So again, a lot of automotive companies, they actually, especially startups, they want to promote end-to-end systems where we collect data from experts and then simply fit a neural network between the sensor measurements and the control inputs. And we will see that this can work up to some extent, but eventually there are going to be cases when this stuff is going to fail. And the question is, if they fail, if our expert end-to-end is failing, can we actually fix that with reinforcement learning? So we will see that this is going to lead us into some interesting outcomes. So these are the three things that we are going to look at. I know we are a little bit constrained on time, so I'm going to do this as quick as possible. And if you have any questions, of course, we can discuss later. Okay, so I'm going to start with fixing the simulation gap. And the problem we are going to look at is reinforcement learning for autonomous driving, especially the problem of lane changing. So reinforcement learning is, like I mentioned, it is basically learning how to control a vehicle based on data. And in this case, we are actually letting the algorithm interact with the environment by itself. Doing maybe a lot of random stuff in the beginning, and then by interacting with the environment and collecting data, it eventually figures out what's a good control strategy to run in this environment. Of course, when I say it begins by doing random actions, we never do that in real life. We always do that in simulators. So in a simulator, you let a reinforcement learning agent run for maybe hours on hours. So in the beginning, it will crash a lot, but eventually it will learn how to drive the car. So this is almost always going to start in the simulator. And maybe we will start with very simple simulators that, the ones that you see in here. But eventually, of course, we want to move in real life. And the reinforcement learning problem that we are going to address here is going to be the lane changing problem. So this is not going to be a low-level decision-making problem. It is going to be a high-level decision-making problem. And the problem is, should I stay in my current lane? Or should I change my lanes in order to increase my speed? And of course, when I do that, I do not want to violate my safety. I do not want to run into a crash. So we want to let a reinforcement learning agent to figure that out for hours, but then we want to run it on real road tests, okay? And obviously, the real road tests are not necessarily going to match the real life conditions. And then what do we do? So this is called the simulation gap. Your simulator which the AI algorithm is trained on is not 100% reflecting what the real life is doing. So our answer to that is basically a closed loop architecture. So what we do is, instead of just training on the simulator and go and test it on real life and end it there, we actually close the loop. After we train everything on the simulator, we execute real world tests, and the data that we collect from the real world tests, we go back to our simulator and we update our simulator to make the dynamics of the simulator look more like the real life. And the key component here is we are actually updating the dynamics of the simulator, not necessarily the graphics of the simulator. Because sometimes when people think about realistic simulators, they only think about the quality of the graphics, but that's only one part of it. Actually, when you want to train a realistic reinforcement learning agent, the vehicles, the surrounding traffics, they need to act like real traffic. They cannot be simply, super straightforward pre-programmed agents. They need to act like humans. And how can we get human data? Well, we can go and do real life tests. So this is how we run, how we actually train our reinforcement learning algorithms at Eatron Technologies. So here I'm going to show it to you, phase by phase. First, of course, we got the initial simulator training. And sorry, so let me go in here. We do the initial simulator training, and then we go and do the real world tests. And after we do the real world tests, we are going to actually acquire a lot of data regarding our surrounding traffics. For example, we are going to get a distribution on what are the lead vehicle positions, what are the distribution on lead vehicle velocity, etc. So this kind of statistics actually gives you a pretty good idea on what are common traffic parameters, like what kind of traffic I can expect when I go and do this kind of road tests. So then we simply took these parameters and update our traffic simulator to match the real life. And then once we do that, we simply get a much more realistic traffic behavior in our simulator. And bar simulator, actually we have two simulators. The first one is a low fidelity simulators where we do not care about graphics or most of the low level dynamics at all. So this type of simulator is more like a computer game, a very simple Atari game actually, not even a computer game. But we need low fidelity simulators because they are super fast. Simulating stuff in here is very cheap, and reinforcement learning agents, they usually need millions and millions of samples to get into some level of accuracy. So first we got this Atari-like environment where we train our algorithms. And of course, this is very crude, this is very simplistic. Then we go into more realistic simulators, which is again our own original software called SimStar. So, oh, there's music, sorry. And in here, all the cars in here, they are not simple models anymore. There's actually dynamics, the road conditions and everything, even the perception system, everything is simulated perfectly in here. And you can also do hardware in the loop tests in here. So after we validate our algorithm on this setting, now we say that, okay, now the car is ready to be run on the actual road tests. And then we go and perform the road tests. Then after a couple of iterations between the real life and the simulator, then everything is amazing. So we have done this, hundreds of times. I do not remember the actual statistics now, but this has been validated on both roads of Istanbul and United Kingdom, and our lane changing performance, the lane changing capability, improved significantly after we started closing the loop. So one way to ensure the safety of the simulator is to make the simulator look more like real life. And how do you do that? By adaptively changing your simulator. So this was the main takeaway we got from this experience. Okay, I'm going to move into, and by the way, this is probably going to be published soon. So please follow us on social media or our website. So when this is published, you should be able to see the whole algorithm and the performance statistics. Okay, the second thing I want to talk about today, these are actually more preliminary works. Unfortunately, we don't have real world driving tests yet, but nevertheless, there are some very interesting results. The second one is, how do we fix RL agents? So the problem that we are going to look at here is, again, one of the most simple but core autonomous driving problems, the ACC, adaptive cruise control problem. It is just longitudinal control problem where we got an agent in here, the autonomous driving agent, and we want to simply maintain the speed and acceleration of this vehicle so that there's almost always a set amount of distance between the leading vehicle. And when you look at this problem, you will see that there are basically 5 different parameters that define the initial conditions of a simulation. You got the distance between the cars, you got the initial speed of the ego vehicle, you got the desired speed of the ego vehicle. Well, the front vehicle, we are not going to assume that it is static. I mean, static as in it is not accelerating. So that would make the things very simple. So instead, we are going to assume that this thing by itself is also running an algorithm. So something like IDM, for instance, and it also has an initial speed and desired speed. So we are going to assume that the car in front of us is also doing some kind of interesting acceleration or deceleration. So depending on how you initialize these parameters, you are going to run into millions of different ACC scenarios. And we want to basically answer the question, given that I have an RL agent or any kind of machine learning agent, actually, it doesn't need to be a reinforcement learning agent. Can I find the scenarios where my current ACC is going to fail? And then can I fix my ACC by retraining my machine learning algorithm on the failed scenarios? So that is the basic idea, very simple. And of course, our performance metric in this case is going to be the time to collision. And if you've worked with ACC systems before, you know this parameter very well, but it's basically, if everything is kept constant, how much time do I have till I hit the vehicle in front of me? Obviously, you do not want this to be a small number. You want this number to be large. But at the same time, if I am looking for the failure scenarios, I am looking for the scenarios where this thing is small. So I want to discover the scenarios where this thing is minimized so that I know they are dangerous and I want to get rid of those. And in this case, for this particular study, of course, whenever we are doing sampling, we need to put lower and upper bounds on the parameters. For the front vehicle, we will say that we will be between 10 to 40 meters and initial velocity is going to be between 50 and 30 meters per second. And the rest of the parameters are here. And our simulation environment is again going to be an advanced simulation environment where we can actually simulate the physics and sensor capabilities as well. And for detecting the failures, we are going to use the sequential Monte Carlo and cross entropy methods. And these methods already exist, taken from other works that I have mentioned before. And one thing that we immediately see, these methods, the cross entropy or the Bayesian methods, which I would call smart methods, they are actually great at finding these failure scenarios compared to other methods. For example, if you do simple Monte Carlo sampling, so if you go and randomly pick, let's say 1,000 parameters, only a very small fraction of these parameters would be the failure scenarios, okay? So by just looking at randomly in your scenario space, it is actually very difficult to find those failure scenarios. But if you do, more intelligent methods such as cross entropy or Bayesian sampling, you will see that by using less amount of samples, you can actually get higher percentage of scenarios where the scenario is failure. Okay, so we are not really interested in finding the good parts. We are interested in finding the dangerous parts. And you can see that by simply switching your algorithm, you can do more intelligent sampling and detect those failure scenarios. So since the time is limited, I'm not going to go through all the plots. I'm just going to give you the main message. And if you're interested, we can discuss later. So what we do in this work is we run all these algorithms, we collect these scenarios. And after we collect this library of scenarios, then the question we ask is, okay, so given that these are my failure cases, how should I retrain my algorithm so that it doesn't fail anymore? And there are, different things that you can do at this point. And for example, you can look at each sample scenario and you can, for instance, merge all of them into a gigantic, training library, and then you can train your algorithms on everything that you have seen so far. Or you can actually give more priority to latest scenarios, because the scenarios which are sampled later are more likely to be the dangerous scenarios. Or you can only train on the latest scenario. And our experience and our results actually tell us that it turns out that the best sampling strategy is not actually to combine everything together, because you will be getting a lot of useless samples here and as well. But instead, use a weighted sampling strategy where you are giving more weights to your samples from later phases of the training, so that you are more likely to sample failure scenarios, but do not get rid of all the old data, keep them as well, but only give less weight to them. So for instance, this is what the sampling looks like. For example, first we sample, let's say 100 different scenarios, and you see a lower dimensional part of our scenario space. For example, this is the speed difference between ego and front vehicle. This is the distance difference. Sorry, the z-axis is the distance difference. This is the difference between their initial speeds, and this is the distance between, the difference between their target speeds. And after we sample 100 scenarios, the orange scenarios that you see in here are the scenarios that we fail. Okay, so what you do in here, once you discover the scenarios that we fail, now we go on and train our algorithm on these failed scenarios, and then we do the sampling again. And very interestingly, you see that these parts of the state space, they are safe in the second step because we fixed them. We trained our algorithm, but now our verification algorithm discovers new parts of the state space where the algorithm is not safe anymore. So this is the nice thing about fixing an algorithm, because once you fix it, now you know that part is safe. In the next iteration, your sampling algorithm will find new parts of the state space that you didn't know about that was unsafe. So this adaptive safety strategy, as you increase the number of iterations, it is going to increase the performance and the generalization and safety of your algorithm. And our results, for example, when we look at very, very hard scenarios, the initial agent, it crashed almost on all the scenario. But if we fix our agents in the very hard scenarios, the number of crashes went down by almost 10%. And when I say very hard, I'm actually talking about very hard scenarios. Maybe even a human driver cannot get out of the scenarios where the distances are very close, or the cars are closing on each other on very high speeds. So you can detect edge cases and fix those edge cases using this type of strategies. But of course, these are just very preliminary results. We are still working on this, and hopefully, we will be able to present even better results in the future. And for instance, if you compare the performance of the algorithm in the first iteration and the last iteration, you actually see striking differences. For example, the blue line that you see in here, this is the performance of the ACC in the beginning of the training. So you can see that the position between the cars, it tries to close it. It actually gets very close to the car in front of it and then tries to settle down for a lower distance, okay? So, but then after we fix the agent, after we retrain the agent, it actually discovers that instead of doing this, overshooting type of behavior, it instead settles down into a much safer behavior. So you can actually teach your algorithm to be more safe by using this, iterative tightening, fixing algorithms. Okay, so the final part. So finally, I'm going to talk about end-to-end systems. So in case you haven't heard of it, so an end-to-end autonomous system is where you are getting your sensor inputs and then you are passing them through a neural network, and then you immediately extract, for instance, the steering and speed output of a car. So it is called end-to-end because this bypasses the whole, control and perception stack. So your perception, decision-making, control, whatever, everything is just bundled into a huge neural network. And then how do you train this neural network? Well, the most straightforward way to do that is by using supervised learning. For example, we can let an expert driver drive our car, and then we will get a lot of data from our sensor inputs, and we can record what did the expert do when they see this kind of inputs. And then we would have this huge supervised data set, and we can then train an algorithm. And it turns out that if you collect enough data, and if you actually let the expert direct you when the algorithm is not doing well, you can get very good results when you do that. So this is a very early result from my lab, probably 3 years ago, from a paper we published at IROS. So we basically show that if you use the expert in the loop carefully, then you can actually imitate what this expert driver is doing very closely. So you can see that this car, it learns how to accelerate, it knows how to decelerate, it learns how to drive it by itself, at least in the simulator. And it is actually impressive that you can do this in an end-to-end manner. Okay, but even the expert drivers, they are going to fail at some scenarios, especially if we are trying to imitate an existing autopilot or something like that. So if we find an instance where the end-to-end is failed, how do we fix it? So that's actually an important question. So the architecture that we developed is, it's a bit complicated, but I will try to explain this simply. So first we learn how to imitate the expert driver, and then we try to run our expert on a very complicated urban scenario, for example, a scenario that you'll see in Carla. And then whenever our algorithm fails, we take that failure scenario and isolate it and create what we call a mini scenario, which just simulates those failure conditions. So this mini scenario, which is simulating our failure, then we retrain a reinforcement learning agent on top of that. So the idea behind that reinforcement learning agent is it should be a specific agent that just solves this type of conflict. And then after we train this agent, it becomes a part of our planning library. So whenever next time we run into a failure scenario, we ask the question, do I have something in my library that can resolve this kind of conflict? And then if we do, then we take that agent from our library, we execute it, and then we see that we can actually resolve that edge case, resolve that scenario. If there is nothing in our library which can resolve that scenario, then what we do is we simply say that, hey, this is a new thing that I haven't seen before. We isolate that scenario, and then we retrain a new agent. So we keep expanding our library. So whenever there's a failure, we create a new agent for it, basically. So since there's not a lot of time, I'm going to skip all of this and just show you the results. So this is the expert driver, expert neural network agent, learning in the simulator. And you can see that it learns how to stop at lights. It learns how to take intersections. Whenever there's a pedestrian, like a cyclist, you can see in this case is in front of it. It can detect it and and then it can learn how to stop. So you can see that some of the basic driving capabilities, it can be imitated very well with the expert driver, with the imitation of the expert driver. Okay, but the problem is even this expert driver, it is not 100% safe. There will be a lot of scenarios where this thing is going to get stuck. So what we do is whenever we identify a stuck scenario, like I mentioned, we run this architecture, we isolate that scenario, train an agent, and then we now have a library of how to solve conflicts, and then we execute that to overcome that challenge. And in this case, for example, let's look at this scenario. In this scenario, experts, so there's a car in front of it, but our expert data actually never seen a situation like this before. So it simply gets stuck. So our expert driver, there weren't any cases in our data set which tells us how to handle this type of scenarios. So it doesn't know how to make a right turn to get ahead. So here we isolate the scenario, we give it to a reinforcement learning agent, and you can see the results on top. So whenever your current algorithm is not working, we go to our library and we execute the algorithm which can solve the conflict. And then you can see that we can basically fix the shortcomings of our current algorithm. Okay, so I want to briefly wrap up the presentation. So what I wanted to highlight is verifying complex autonomous decision-making systems is very hard. And we definitely need to go beyond our current toolset because, like I mentioned, our current toolset does not handle verification of complex systems. It cannot handle it very well. So algorithmic and sampling-based approaches can actually help us navigate this enormous search space. And not only they can help us navigate, they can also help us fixing those failures. But still, a lot of work needs to be done. And as you have seen, there's a lot of simulation tests, but not a lot of hardware tests. So that is a thing that we are actively working on. So we basically need to verify the verification algorithms. So we need to verify that our algorithmic verification is actually working. So there's still a lot of work to be done. But I think this is a very promising and exciting research and application area. And as you have seen, this doesn't actually need to be just for autonomous driving. Any system that you need to verify safety, for example, something like a BMS system, you can also use these methods too. And before I wrap it up, I also would like to thank my collaborators. So as a director and a professor, I am lucky because the 90% of the stuff that you have seen here is actually not done by me. It is done by my colleagues. It is done by my students and my fellow researchers. So I would really like to thank Uğur, Resul, Halil, Burak, Anil, Melih, and of course, our CTO, Can Kurtuluş, for all of their support and input. And I would like to thank you all for patiently listening to me. And if you want to reach out to me at any time, my email is there. Thank you.